Okay, now let's add another step to what we've done previously on free body diagrams. So we have a situation here where we're going to have motion that's going to occur. So we have a car of mass 1682 kilograms, won't start, so two people are pushing it out of traffic. There are two different people pushing it. One of the people is closer to us, one of us is further back. Okay, we've got the forces that they're applying, and we also know there is a frictional force that is acting on the car. We want to draw a free body diagram and then calculate some of the force values. So, free body diagram, I'm going to draw, use your imagination here. There's our car that's being pushed and our coordinate system on which we will draw all the forces. So then acting on this car, we've got the two people. The person that is closer to us applying a force of 220 newtons at 25 degrees below the horizontal. So we can see the man in the front, his arm goes downward. And so I'm going to draw that force right here. And again, that is 220 newtons at 25 degrees below the horizontal. The second person is applying a force of 175 newtons horizontally. So there is our 175 newton force. Now, in addition, we need to consider the other contact forces and field forces. Field force, we always have the weight of the car acting. So F sub G, and we know how to calculate that. Weight is equal to mass times gravity when we need that. The ground is in contact, and the ground is applying two different forces. The contact force of support, or F sub N, the normal force. And then we're also told that there is a frictional force that is acting. So then this is our free body diagram. Now, in part B, we want to calculate the magnitude of the frictional force. So, magnitude of the frictional force, well, that's a horizontal force. So then what I'm going to do is I'm going to look at all the forces horizontally, because we're told in the problem that the car moves at a constant velocity. If it's moving at a constant velocity, then we have a situation of equilibrium. And being that we have equilibrium, it means we don't have any extra newtons. So when we add up all the horizontal forces, we know we're going to get a zero. If we didn't get a zero, we would have a change in motion or an acceleration. So then we're going to use this to be able to solve for the frictional force. But what we have to do is get all of the horizontal forces. Well, we know we also have 175 newtons from our free body diagram, and then we have the 220, but it's at an angle, so we're going to have to do some trig on that initially. So I'm going to draw separately over here our 220 newton force at our angle of 25 degrees, and then I'm going to do trig on that. I'm going to get our x and our y component. So that'll be a sine and a cosine. Cosine 25 degrees, adjacent side x, over hypotenuse 220 newtons, and then sine of 25 degrees. That's going to be the opposite side, which is y, over 220 newtons. So if we calculate those values, my x component's going to give me 199.38 newtons. And for my y component, I'm going to get 92.97 newtons. I'm going to draw those back over here on the diagram. So then the horizontal component right there, that was our 199.38 newtons. And our vertical component, I'm going to draw back over here so that we keep track of it with our other vertical forces. 92.97 newtons. So then basically we are replacing the 220 by these two component values. So then if you like, you can scratch that out because we're no longer dealing with that value, just the components. So now when I gather up all the horizontal forces, I've got these two that are moving to the left. So then those are going to combine, those are going to add, and then friction, which is in the opposite direction. So then I'm going to go left, negative 199.38 newtons. Also left, negative 175 newtons. And then to the right, positive frictional force. That's all of my horizontal forces. And I combine them to get a 0. So these two they have the same sign, so they'll combine, they'll add together, and then we're going to add that to the other side since the total there will be negative, and we get the force of friction to be 292.36 newtons. Now, you can write out a direction on this if you like. We already have a direction drawn on the diagram for friction, so then it's optional if you write out the direction to the right or not. Now, part C, calculate the magnitude of the normal force. So if we're looking at the normal force, that's a vertical force. So then, just like we gathered up all the forces horizontally, I'm going to gather up all the forces vertically. Vertically, the car is also not changing its motion. It's not flying into the air or falling through the ground. And so when I add up all the forces vertically, I should get a 0. We look back at our free body diagram, we've got the normal, we've got the 92.97, and we've got the weight. So then that's going to compose my equation of all of the horizontal forces. Normal is upward, I'm going to call it positive. 92.97 is downward, negative. And then the weight, mass times gravity. Up here, given in the problem, we know that the mass is 1682 kilograms. So I'm going to plug in values for M and G. 1682 kilograms times 9.8 meters per second squared. That is all of our vertical forces. So then we'll multiply the 1682 times 9.8. And then we'll combine the negative 92.97 and the value we got when we multiplied and solve down for the normal. We get a normal force value of 16,576.57 newtons. Again, our diagram shows the direction of that to be upward. So then we drew our free body diagram. We did the trig. And then we sum the forces to be able to solve down for our unknowns. Ponder physics.